let's get going with the second part, which relates to the first part. So layer two. Layer two, which is the data link layer. And we said the most important thing out of that is that knowing that it's a user frames as the protocol data unit. It uses MAC addresses as the addressing system, and what was it? The switches are devices which operate at layer two, which is a data link layer. So let's talk specifically now about Ethernet switching. So I think I've sort of described that in the first lesson, but let's actually get into the actual PowerPoint that talks about it. So remember, if you remember, in the first lesson, I was trying to set the scene and gave you a bit of a big picture how it works. And let's talk about some of the more specifics. So Ethernet switching, today we're going to look at the Ethernet frame specifically, because that's the one we're most likely to deal with. And we're going to let the Ethernet MAC address and look at places where we can view this. And we're going to look at the MAC address table that we referred to earlier in the first lesson. And we can use that to actually identify what MAC addresses the computer knows of. And we'll look at some of the switch forwarding methods and the port settings that are available in our layer 2 switches. So Ethernet frames. So we sort of looked at some diagrams with the headers and the trailers and all that kind of stuff previously. But if we look at this diagram, the Ethernet is 802.3 and the 802.2. So Ethernet operates in the data link layer and the physical layer. It's a family of networking techniques defined by the IEEE. So that's the International Electronic and Electrical Engineers Society, and they make these standards. As we know, standards are the things that make things common. How do we all know to drive on the left-hand side of the road? It's because that's the standard for Australia. If you take that, if you're from America, for example, and you're used to a different standard, and you try to apply those standards in this country, you're going to have accidents, aren't you? So basically, as long as everyone's obeying the same standard, then all things work together. Okay. So if we look at this, so we referred to this already. We referred to this already in the first lesson, but let's have a quicker look. Okay, so it talks about bytes. If you remember, a byte is 8 bits. So if we're talking about 8 bytes here, that's 8 times 8 bits. We don't need to know these numbers that well, to be honest, not to pass this subject. But obviously, if you're an electronic engineer and you're designing some of these things, and you're designing your system, and you're building a new piece of hardware, and you want to make sure that it follows the standard, and you want to use these areas to read these areas and use those information, then you must obviously know these bits of information. But unless you're doing that, you really don't need to know how big each of these sections are. Okay, so a Ethernet frame has various fields, and they contain various bits of useful information. And the minimum size for an Ethernet frame is 64 bytes. Okay, and the maximum frame is 1,518. These two numbers, again, you don't necessarily need to know exactly the numbers, but just know that anything that's below 64 is illegal, as in it won't be detected as a proper Ethernet frame. And sometimes when you have problems with your hardware, like your network card has a fault, it has a fault. It's like intermittent fault. It can just send things or cause signals transmitted on the wire because of this intermittent fault. So sometimes these network cards are referred to as jabbers. They're constantly talking. It's like someone who just can't be quiet. They're just constantly talking to themselves or something like that. Okay, but they can cause, obviously, in a situation where we're using that carrier sense multiple access collision detect, if they're constantly doing, no one else can get a word in, can they? All right, so they're wasting the bandwidth. But if they're 64 bits, it'll be detected as one of these illegal frames, and it would just be ignored. And the maximum is 1,518. Anything bigger than that is also illegal. And it's just like your semi-trailer we were talking about. There's only a maximum length. the trailer can be. If you exceed that, then the cops are gonna pull you over and say you're breaking the law. In this case, we're gonna like a giant. So the smaller frames are sometimes called runts or collision fragments, and the large ones are jumbo or baby giant frame. So these are some names that we give them. Any frames less than 64 bytes is considered a collision fragment or a runt frame, and is automatically discarded. Frames which are more than 1500 bytes of data are considered jumbo or baby giants. The size of a transmitted frame is less than the minimum or greater than the maximum. The receiving device just drops it, just ignores it, because something obviously went wrong. So why is it small? Maybe because something interfered with it and you just got a little bit of it. Why is it too big? Maybe one frame got merged with another frame because something again happened. Like maybe there's a bit of electric magnetic interference in the middle of the wire somewhere, and it's caused some changes and it's made two merge together and you got a giant frame. So in that case, why waste your time dealing with those things? They're illegal, just ignore them. Okay. They are considered invalid. Jumbo frames are usually supported by fast Ethernet and gigabit switches and NICs. So if we keep on going, so this is the areas, but the key parts that we need to know is this destination MAC and source MAC addresses. Where's it going? Where's it from? And obviously the data, but the last bit, just be aware this is FCS, that's a frame check sequence. Remember how do we know this frame has been corrupted or not corrupted? If we do this algorithm, it should end up with this result. If we do the same algorithm when we receive it and it doesn't end up with exactly the same result, then something's gone wrong and it's considered rubbish. Okay. The MAC address. Like I said, it's a hexadecimal. It's probably a better way would be to just show you some MAC addresses. So if we look at my command prompt on my real computer, hopefully you guys can see it from where you are, but maybe I'll just change the properties. I might just change the fonts to be 36 maybe. All right, maybe a little bit better. So if I do an IP config, so you probably should be familiar with this command now, IP configuration basically, and I do the IP config all. Okay, so all, I might just find the one that's plugged into the real network. So you can see that this one, the specific DNS suffix is adl.tafesa.edu.au. So that I know is the one that's plugged into our real TAFE network. You can see I've got a whole heap of them. And that's because I've got some which are virtual Ethernet adapters. So that's from the VMware software. When we create virtual networks, we could get virtual adapters as well. We also have our wireless network. Remember that 802.11? Okay. This is, you're probably thinking, hey, that's pretty old, but if you look at the next part, it's AC. So that's one of the newer standards. We also have, I think, Bluetooth somewhere. Yeah, here it is, Bluetooth for PAN. You probably heard of LAN and WANs. So the LAN is local area network, WANs, wide area network, PANs, personal area network. All your devices that you connect via Bluetooth, such as my headphones, your Bluetooth speakers, your watch, pretty much everything that you use on your, like I'm sure you have headphones. I'm pretty sure everyone here has got a set of headphones and probably in their pockets with that, with Bluetooth. So if we look at the physical address, so the MAC address is referred to as a physical address. So you can see that that's a hexadecimal. I know it's hexadecimal because it's got numbers and letters. And those letters cannot be bigger than F. Okay? So that's a hexadecimal code. So that's my MAC address for my computer. I'm guessing most of your computer will have something similar. I think most of your computers will have something that says 6C4B990. Can I get you guys to go check? Sorry, 94 as well. So can you get all of you guys to check on your computer, start a command prompt, do IP config, find one that's connected to the adelaide.tafesa.edu.au. Look at the physical address and tell me if it's different to 6C4B0. Okay, so if anyone has something different than those digits for the starting first half, let me know. Anyone got anything different? Anyone not able to find the MAC address of their own computer? So you just need to start up a prompt. All good? Anyone having big problems? Okay. So anyone find any MAC addresses which are different to these? All right. So I'm also guessing all of you guys also says Realtek at the top, just above it. Is that correct as well? Yeah. You know why I know that this is true? Because all of these computers are identical. They're from the same manufacturers, and we've got the same hardware specifications. So Realtek is a company that makes devices, and this first half of the MAC address represents the company, the vendor. The second half MAC address should be different. Okay, maybe there's some things which are the same, but essentially the combination will be different. Okay, so let's actually show you this. If we go here, we go MAC address, vendor codes. Okay, vendor code search. Let's do a search. All right, let's go to the vendor. So let's say I didn't know it was a. Let's say I didn't know it was a Realtek because for some reason it didn't come up. If I just plug in my MAC address, like I just copied it out of my command prompt just then, and I, oh, come on, okay, yeah. So this is actually coming up as Lighton. Okay, I'm not sure if how the relationship between Lighton and Realtek, it might just be their partnership. But if do we have another Mac? Do we have another one? Let's go and look at our Bluetooth. Actually, let's look at our VMware one. So if you look at this VMware MAC address here, let's look that up. So VMware is not a manufacturer, obviously. It's a company, but you notice that it comes up as VM straight away. You know why? Because the virtual machine still can actually go onto the physical network, can't they? With the bridge network or the NAT network. Actually, bridge network is probably more important, but this is coming up as VMware. Because again, these MAC addresses or these codes are assigned to the companies. Okay, so that's more like it. Let's have a look at my last one, which is the Bluetooth. Where's my Bluetooth? Here we go, physical address here. Let's find out. It doesn't say the company, does it? So let's find out what it is. All right, so let's find out. Not sure. Let's plug in the MAC address. It's a Cloud Network Technologies Samoa Limited. So wherever that company is, I've never heard of that one, to be honest. There's probably plenty of different companies around the world I haven't heard of, but I can find that. Let's go. Let's forget about the search. ID list. All right, so no. So if we go to this one, you can see that this is the first half of the MAC address. So 1, 2, 3, 4, 5, 6 hexadecimal numbers. And let's see if we can find VMware. There you go, 000569. Let's go have a look at our VMware. Where's the VMware adapter? Virtual adapter. No, not this one. Let's see if there's any more VMwares. So there's 4. So don't forget that just because there's another one, 0C29, 001C14, and 005056. I think that one was it, wasn't it? 005056. So basically, a MAC address is hard coded. Okay, so when you go out, buy a computer, buy a network interface, the MAC address is on there. You don't configure it. It should be different because, like I said, first part is the vendor who made it. The second part is a unique one from them. So you shouldn't have to do anything with it. But what if I did want to do something with it? What if I want to be a little bit sneaky? That's probably most situations what they do. What if I want to be a little bit sneaky and I'll just mess around with the VMware one? And what if I just want to configure a specific MAC address? Because I want to test the MAC address filtering on my Wi-Fi network, for example. I might just go to the advanced, where was it? Jumbo packet. So this is talking about the jumbo packets. It's advanced Wacom LAN drivers details. That's device is working properly. Let's try this one. Yeah, here we go. Okay, so this has a little bit more, and I think there is one in here somewhere. Network address, and instead of actually using the one that's on your card, I can actually just type in a MAC address here. Oh, so that's not a full MAC address, by the way. Is it? Yeah. So I can do that, and that's what's called MAC address spoofing. Okay. So some people might want to spoof their MAC address for various reasons, nefarious sometimes just for testing, but you can. But normally you wouldn't have to do anything with it. So Ethernet MAC address consists of 48 bits of binary values expressing using 12 hexadecimal values. Given that 8 is 1 byte, is a common binary grouping. Yeah, so from all zeros to all ones, and they can make us any arrangement. But so what does that mean? The hexadecimal, if you remember, the lowest number you can have in the hexadecimal is 0, obviously, but the highest one is F. Okay. So it can range from 00 to FF. When using hexadecimal, leading zeros are always displayed to complete the 8-bit repetition. For example, if you have a binary value of quadruple 0, 1010, it's represented in hex as 0A. Okay, if we did a conversion, we'll end up with that. Hexadecimal numbers are often represented by, so if you see something that goes 0x something, the 0x basically means what follows is a hexadecimal number. Because if I look at that 73, if it didn't have that 0x there, I could just think that's a decimal number, couldn't I? But because of that 0x, that's actually a hexadecimal 73 instead of actually a decimal 73, which has a totally different value. Hexadecimal may also be represented by a H, so 73H, H for hexadecimal. So if you see that, that also means that. So Ethernet MAC addresses, like I mentioned, the first half is an organizationally unique identifier, so it goes with the vendor, the manufacturer of the card, and the second half is a vendor assigned, which basically is a unique sequence that's given to the individual devices or part. Frame processing, when a device is forwarding a message to an Ethernet network, the Ethernet header includes the source and destination MAC addresses. So we've mentioned that a few times now because that's one of the most important things. When a NIC receives, what a NIC is network interface card, just in case I haven't explained that before, receives a Ethernet frame, it examines the destination MAC address and assesses whether it matches its own MAC address. So how do I know this letter is sent to me? It says my MAC address on the front. Is that my MAC address? Yes, that must be for me. But you know what? If it's not my MAC address and I got it, well, just like you would treat a real letter, you wouldn't open a letter that's not addressed to you, would you? Yeah, it's not mine. I'll just ignore it. So that's how computers work. But obviously, sometimes we do want to open letters that's not ours because we're snoopy, aren't we? We're a bit snoopy. We want to see what's going on the network. Maybe we're using Wireshark to just see how things are, what things are flowing through the network. So maybe I might put my network card into what's called promiscuous mode, which means I will look at everything, not just the frames that's destined for me. All right. So basically, if there's no match, the device discards the frame. If there is a match, it passes on to the frames up the level so we can look at the data. Ethernet NICs will also accept frames if the destination address is a broadcast. So you might have heard of the term broadcast, unicast, multicast. We spoke about that in terms of IP addresses. So if you see a MAC address which is all Fs, all of the characters are Fs, that's what's called a broadcast MAC. So if that's in the destination address, then any device will see it as, yes, that's me, I'm part of everyone. So that's for everyone, so I'm part of everyone, so therefore I will look at it. So the broadcast MAC address. Any device that is the source or destination of the Ethernet frame will have the Ethernet will have an Ethernet network interface card and therefore a MAC address. This includes anything, including, just like I said, my headphones, my mobile phone, my watch, and any other device that is got Ethernet. So unicast MAC addresses. So if it's a unicast, it's one-to-one uni. Okay, so that unicast is where you have a unique MAC address. In Ethernet, different MAC addresses are used for layer 2 casts, broadcasts, and multicast functions. A unicast MAC address is a unique address that is used when a frame is sent to from a single device to a single destination. The process that a source host uses to determine the destination MAC address is associated with a IPv4 IP address. So let's just describe a problem. I want to go to the website that's here. I know the web server is 192.168.1.200 because we all use IP addresses to communicate. We use DNS to communicate. If you remember my example before, if I want to go to, let's say, a google.com, I would do NS lookup google.com, and I will get an answer. My answer is an IP address. Okay? If you're wondering what the hell this is IPv6 IP address, or IP address, but let's stick with IPv4. I'll get an IP address. Computers use IP addresses to communicate. But if I'm on a local area network, let's say this server's on a local area network, I also need the MAC address, don't I? Ooh, so how do I find that out? Basically, there's this protocol called ARP, Address Resolution Protocol, and we basically broadcast to everyone, who's got this IP address of 192.168.1.20? And obviously, if Josh over there has it, what do? You say, I do, right? But when you reply, it's in the form of a frame, isn't it? Because that's encapsulating his message. When I look at the frame, I look at the source and destination MAC addresses, and from the source address, I can see that Josh's MAC address is this. So that's how I find out what the MAC address is. I ask everyone, who's this address, and they reply. Only one replies. The person who replies is the one with the IP address, obviously. So let's have a look at this. So ARP is the command. Is the address resolution protocol. If I do ARP, let's have a look at this one. Okay, this is the TAFE network, I believe. Okay, so Adam, have you got your command prompt open? Can I get you to open it and give me your IP address? All right, so basically you can see there's an IP address to physical address mapping. These are all the MAC addresses that my computer's learned. Yep. Okay, you can see on my list there's no 10.62.29.33, is there? Because my computer's never communicated with Adams since it's been turned on. So this is all in memory, so it's temporarily stored. It learns it every time. When you turn it off, it gets wiped. Even when the time expires, it gets wiped. But when I try to ping Adam's computer, he's blocking me. Oh well. Let's have a look. What's my IP address? Am I even on the same network? So the other thing. Remember, MAC addresses are only used on the LAN, not between LANs, between networks. So let's actually have a look at my again. What's my IP address? Mine's 3.1. That's let's see, IP config. So I think my example failed because I'm on a totally different network. That's not very good. All right, so I might have to. How can I demonstrate this? Is anyone else on my network? No, I bet you I'm on a different network because this is a computer that is electric computer. What can I do? What can I do is I can start up a virtual machine.
You can try again.
Sorry?
You can try again to ping
him, but he's not on my network. It doesn't matter if I can ping him or not. I'm not going to learn his.
Sometimes after the first time,
yeah,
he's learning the process.
Yeah, no. He's on a different network, so therefore I would have to go through my router to get to his computer. So if you remember, the MAC address does not cross routers. The MAC address is only for this LAN. So wherever I do, if it goes through a router, it's only got to give me the MAC address of the router. You see this? This first one is the MAC address of the router, 3.1. So I'll never, if we're not on the same LAN, I'll never be able to learn his MAC address because basically MAC addresses does not traverse different routers. Let's tiny 10. Let's have a look at that one. Hopefully I can log in. All right, so while that's loading, let's continue to look at the PowerPoint. All right, so we're up. Okay, so the broadcast MAC address is all Fs, like I mentioned. That's effectively all the binaries are all ones. The multicast MAC address, if you forgot what multicast is where you're communicating with multiple computers, a group of computers, not all computers. Ethernet multicast frame is received and processed by a group of devices that belong to the same multicast group. Okay, there's destination MAC address is 01005E when the encapsulated data is a IPv4. There are other reserved multicast destination MAC addresses as well that is not IP, such as the spanning tree protocol. So if you've never heard of spanning tree protocol, it's just a Cisco protocol that switches use to communicate with each other so that they do what's called a switching loop, where if you have multiple interfaces connected to the same switch, you could do a loop, couldn't you? You keep on forwarding. Because multicast addresses represent a group of MAC addresses, sometimes it's called a host group. they can only be used as the destination of a packet. The source will always be a unicast address. Let's go have a look at my tiny 10. Win10 tiny. So hopefully I'm logging in. The other thing I would check it's NAT, so it can't be NAT. I'll make it bridged. So bridged instead, and I will check CMD ipconfig. Is this connected? Yeah, no, it's connected now. It's just got connected. Yes, okay, it's 3.47. Okay, so let's go back to my example, which failed miserably just before. So let's clear the screen and reset the stage like it never happened before. Up, -A. If we look at this interface, oh no, it's just learnt it. It's just learnt it there. You see that 47? It came up, it must have communicated, and it just learnt it in my table. But that sort of shows it anyway. But before, you saw that there was no 47, was there? Remember that? We only had the .1, which is the gateway. But now, because I've turned that on and because there's a virtual machine on here and because of all those reasons, I just learnt it. It's dynamic. These things are learnt dynamically. Dynamic means they are changing. So next time might not be here. Okay, I've learnt it. Let's just prove I learnt it, because if I look at last 2 digits, 91. Let's find out if it is, in fact, this computer. If we go here, if we go to the MAC address, oh, look at that, 91. Okay, so even though it didn't learn it when I wanted to learn it, it actually learned it as I described it, but it just did it at a different time than when I was trying to do it. Yeah.
If it wasn't there, would you replace with the ARP command, like with the A?
Yeah.
Would you just replace it with an IP address, or?
Sorry, say that again.
So
if it wasn't here,
how would we actually find it?
How would we find it? So we would do anything that causes a communication. So if I needed to communicate with another device, before I can communicate, it will have to look up the MAC address.
So when you did the ping,
yeah, when I did the ping, I would have triggered the whole process of the MAC address. So that's why I did the ping before. And by doing the ping, it has to find the MAC address. Once it finds the MAC address, it puts it in here. Okay, so let's do something else. Let's actually. So this is getting a bit too big to read properly. So let me just change the properties. Font. So I'm going to change it to 24. Okay, so if I don't know command, I'll put the /question mark. I think there's a delete. Delete. Oh, okay, let's try that. Deletion fail. Request operation requires elevation. If you remember from Monday, I know you're not there, Javad. Remember how I can start a command? Remember the UAC? The UAC, the command. How can I put it on this screen? Bear with me. Alright, so I'll have to just do it on the other screen, unfortunately. So I type in CMD. Unfortunately, I can't right there, but I can right click on the CMD and I can run as administrator. And then I get this UAC. If you remember from Monday, I have to elevate my privileges, because this what I'm trying to do is going to require that. So you can see that I'm running as administrator. So ARP -D star. A specified entry not found. 8. Geez. Star. All right. So if I do ARP -A now, you can see it's all gone, isn't it? Can you see that, guys? You see that 47 that was there before? It's gone now, isn't it? So I basically deleted it. Deleted the entries. Now I'll do the ping. what was it? 10.62.3.47, wasn't it? Why do you think I'm not getting a reply, guys? People from Monday? Huh? So why do you think I'm not getting a reply? Firewall, correct. So here we can disable the firewall like we talked about on Monday. So see how it's on. But just even if the firewall is blocking us, right? Let's just look at our ARP again. You see that 47 is there now? Yeah. So even though I didn't ping it, I still found out what the MAC address is. Because before I can try to ping it, I had to find out the MAC address. So by the time I get a reply, so I'm already trying to ping it. I already know the MAC address. So just for completion's sake, for Jivan, who wasn't here on Monday, because he's not in that class, I'll turn off the firewall on this destination. And we'll just show you that by turning off the firewall, now I get a reply. So the firewall is actually protecting us by making us stealthy. All right, so continue. The MAC address table. So switching fundamentals. So like I said in the first lesson, when you have a device like a layer 2 switch, okay, they have a MAC address table in there. Our computer has a MAC address table. See that ARP? I just showed you the MAC addresses. So the switch has one, it maps it to the ports, and then only sends the Ethernet frame out of the ports that's mapped up with the destination MAC address. A layer 2 Ethernet switch uses layer 2 MAC addresses to make forwarding decisions, so it decides which port to send it out. Look up the table, it's on port 1, so I'll send it out port 1, because the port 1 has the MAC address of the computer that I want to communicate to. It is completely unaware of the data. It doesn't care about the data, to be honest. It's layer 2. Layer 2 does not look at the data. Layer 2 only looks at the frame and the MAC address of the frame. So being carried, it doesn't care about the data. It doesn't care about the IPv4. An ARP message or a IPv6 ND packet, the switch makes its forwarding decision based solely on the layer 2 Ethernet addresses. An Ethernet switch examines the MAC address table to make a forwarding decision for each frame, unlike legacy hubs, like we said before, that repeats the bits, so they just send it out at all ports, which means everyone gets everyone's. So the switch sends it as the switch sends it only out of the port that's mapped to the MAC address. When a switch first turns on, so you see this switch here, I've plugged something in there, but I shouldn't have. Like, that's actually turned on. It's off, okay? So I'm taking the power out. It's like I've turned it off. I'm putting the power back on. You might see in a minute that these ports go amber. Maybe not. If anything's plugged into it, I guess. It's actually learning. So when you turn it on and you got computers plugged in, it's amber color and a green color. And that's actually learning. Remember how that MAC address table? How does it even get that table? It learns from the communications that's going around which port is connected to which MAC address is connected to which port. Sometimes, so hint, if I were you, I'll write this note down right now. Okay. The MAC address table is sometimes referred to as the content addressable memory. So when you do assignment one of the questions is where are these things stored? Okay, for router, it's the networks are stored in the routing table. For the switches, the MAC addresses are stored in the MAC address table or the content addressable memory. Okay, so that's why I'm sort of hinting, if you get my point. Okay, switch learning and forwarding. So the switch examines the source MAC address and learns. So every time there's a traffic on this, it looks at the traffic going into the port and then looks at the source MAC address, and then it maps it to that port number it's receiving it on. So every time the frame enters the switch, is checked for new information to learn. It does this by examining the source MAC address of the frame and the port number where the frame entered the switch. If the source MAC address does not exist, it is added to the table along with the incoming port number if the source address does not exist. The switch updates and refreshes the timer for that entry. By default, most Ethernet switches keep an entry for about 5 minutes. So it's not forever, it's dynamic. After a while, it just drops off, okay? Because you know what's worse than not having information is having the wrong information. So if it drops off after 5 minutes, then that's fine. If it next time it communicates, we'll just learn it again. All right. You'll probably think you may notice that my computer here has a blue cable. That's an Ethernet cable, and it's plugged into the wall and it's going back somewhere to a switch. Now, if you remember, I've got a MAC address, don't I? I have a MAC address on my. So let's say my computer is plugged into switch 1 of the switch, not there, somewhere elsewhere. Okay. Let's find out my MAC address. Iconfig all. So we know how to find the MAC address out, and my MAC address is this. Okay. If you remember, my virtual machine is also running on this computer, right? And it's got a MAC address of this. Essentially, both these computers, my physical computer and my virtual machine, are all both connected to the physical network through this Ethernet cable, through the walls, and if you imagine, through out of this cable into this switch 1, switch port 1, okay? So what do you think is going to be mapped in switch port 1 in the MAC address table? How many MAC addresses? 2, yeah, you're correct. So just because the MAC address table normally is 1 computer, 1 port, you can map to lots of MAC addresses to the same port. Remember what I said? I could take a cable and connect one switch to another switch. As far as this switch is concerned, all the computers which are up into this switch now are all mapped to this one port. You get me? So if I've got 24 all connected to here, but when it comes out of this cable into this port, it's all going to be mapped to that one port. So therefore, when it needs to send, when one of these computers which are into these switch ports need to communicate with any of these computers which are plugged into this switch, it will always send it out of this port because it's being mapped to that port. So it's not a one-to-one thing. Okay? It's a mapping of any MAC address that's been detected as coming in on that port. If it's 1, it's 1. If it's 20, it's 20. It can be as many as it needs, because we can actually expand our network from one switch to another switch to another switch to another switch to another switch, and we can pretty much daisy chain this network to as big as we like, obviously up to a limit where we can't physically have enough IP addresses or stuff like that. Yep.
So with the MAC addresses, like we talked about overflow,
yeah.
Is there an overflow that can happen to a switch?
Yeah, like I said, in the past, someone could just stuff too much data into that area of memory, the content addressable memory that we talked about, and it will cause a problem where it just works like a hub. But if we're just talking about MAC addresses, the physical and stuff like that, that's not a problem. That's not a problem, okay? So that amount is not a problem. It's the amount is where it's artificially inflated, where they stuff so much it's artificial. You know what I mean? It'll be equivalent to like having all the computers in the universe all jammed into one switch type situation, okay? So it's not going to cause a problem if we just add more and more computers, if that's what you're asking about, okay? That's not sufficiently big enough, okay? And that's how we expand networks, really. when you get to Cisco 2 and 3 in the diploma, you'll talk about scaling switching networks. Okay, so where we have this thing called a backbone network, we have a distribution network, we have a what's a network. So it's a hierarchical and it's modular. We can just plug more and more on, so we can actually scale our network from a small network to a big network without causing redesign of everything. All right, let's keep on going. Note, if a source MAC address does not exist in the table but on a different port, the switch will treat this as a new entry and is replaced using the same MAC address but with a current port number. So what is that saying? So that's a pretty important one as well. Let's say this computer is plugged into, it's coming out of this and it's into port 1. No problems. It's going to map to port 1. Let's say someone like Marianne comes up here and takes it out of the port and plugs into port 23. Whoa, but it's only been a few seconds, hasn't it? It was in port 1. This has been mapped to port 1, but now she's moved it and mapped it, put it into port 23. Now the switch is going to receive communication on 23, and it's going to say my source MAC address is this. Oh, but that's already mapped in port 1. So what happens is that the switch just goes, hey, it's the same MAC address. This is newer. I'm going to delete this one and map it to this one instead. Because of that situation, people can unplug, repatch this in, and that's the whole point of this dynamic network, is that we can actually do all of these things constantly. It can you can learn and get new networks up and running quite easily. All right. I didn't realize that whole thing was on. I just turned it off. All right, so let's keep on going. Switch learning and forwarding. So finding the destination MAC address, the forward part of it. So if the destination MAC address is a unicast MAC address, the switch will look for a match in its table, the MAC address table, and if there's a match, and it looks at what port it's matched to, and it will only send it out of that port. If the destination MAC address is not on a port, not in the table, switch will forward it out of all the ports except for the one it came in on. Obviously, it's not on that one. Otherwise, the would have already talked to it. So obviously, it does. I don't know. Where do I send this? I don't know. I'll send it to everyone. And you're guaranteed to get there, aren't you? If it's on the system at all. Note, if the destination MAC address is a broadcast or multicast, the frame is also sent out all over the shop. That's just, if you think about it, it's just means you're definitely going to get there. Okay. Filtering frames. Okay, filtering means obviously I allow some through and not others. So if I have a water filter, obviously I let the water through and I stop the things like chlorine and stuff. Okay, so filtering means that, letting some things through and not other things. So filtering frames. So that means we're going to look at the frames and we're going to let some frames through and not others. As a switch receives frames from different devices, it's able to populate the MAC address table by examining the source MAC address of the frame. When the MAC address table of a switch contains the destination MAC address, it is able to filter the frame and forward it out of that single port that's mapped to. So if we look at this, port 1, it's sending information in, and it's learned that that's the MAC address is mapped to that. Yeah, no problems. I think we will understand that, don't we? Yeah, all good. But it's going to a computer. So it reads the destination MAC address. Look at that, the destination MAC address 000D. And we go to the table and we go, hey, 000D is actually mapped to number 4, so it sends it out of only 4, not 3, not 2. I think that's easy enough to understand, isn't it? Okay. switching speeds. Okay, so I think that's the. Sorry, my mouse is not good. Switch speeds and forwarding methods. So as with anything in IT, there's always something on speed, throughput, which one's faster, how does it perform, so forth, everything. So let's have a look at this. Frame forwarding methods. So methods are used to decide how it forwards. The switches use one of the following methods for switching data between network ports. There's the store and forward switching. This is where this frame forwarding method receives the entire frame, so it waits for the entire frame. Remember that frame could be 1518 bytes, couldn't it? All of that, it reads all of that. Where does that store? Guys, where is this thing stored? Let me just tell you, a switch, a router, they're basically computers. Where do you store something temporarily? What'd you say? RAM, correct. So this entire frame, I'm going to put in RAM. Okay, so if you think about it, that's a lot of information, isn't it? Okay, I have to wait for all the information to come, and I have to put it in RAM. Okay, no problems. We can do that though. So it computes the CRC, so the cyclical redundancy check. Remember the error checking that we talked about? It calculates that. If it's good, as in there's no problems, then it's valid. The switch will look up the destination address, which it determines the outgoing interface. Then the frame is forwarded out of that port. I'm not sure about you guys, but if you haven't realized, it's doing a lot of work before it decides where to send it, isn't it? So if you think about it, if you have to think that much, it's obviously going to result in some lag, latency. So let's see the cut-through method then. The cut-through method, the frame forwarding method forwards the frame before it entirely receives it. You know why? Because in the header is the destination MAC address, isn't it? I don't need to read the rest of it. I can just look at the header and work out where it's going. Right? That's the shortcut, isn't it? I don't have to wait for all of that. I don't have to store all of that in memory. I just have to look at the first bit of the header to work out the destination MAC address, look it up, and then I can forward it. So this frame forwarding method forwards the frame before it entirely receives it. At a minimum, the destination address of the frame must be read, so which is just right at the start. So the big advantage of the store and so let's talk about the advantages. Advantage of the store and forward switching is that it determines that the frame has no errors, first of all. If there's errors, then I'm forwarding errors as well if I don't check it. So the advantage for the store and forward is that I'm just forwarding frames which do not contain errors. When an error is detected in the frame, the switch discards the frame so it doesn't waste time or effort with the error frame. And reduces the amount of bandwidth consumed because we're not wasting our time with the frames which has the errors. Okay. Store and forward switching is required for quality of service. So remember the quality of service. Remember I said that if you talk about the types of communication, if I'm looking at an email and I'm looking at a live stream of a concert, doesn't matter if my email takes extra 5 seconds, 10 seconds to load, or do you think an extra 10-second lag on a concert would be annoying? Which one is worse? For the concert, of course, because then you can't enjoy it. So therefore, the quality of service recognizes that this type of traffic gets higher priority, and this type of traffic gets lower priority. So if it has the store and forward, it'll read the whole thing. It'll realize this is for a live stream, and it puts it at the front of you. VIP straight to the front. Whereas the email communication, that's low priority. We'll push it back. That's for the cattle class on the plane. So store and forward is required for quality of service analysis on converged networks, where frames classification for the traffic prioritization is necessary. For example, voice over IP data streams need to have priority over web browsing. What about cut through? Okay, in cut through switching, the switch acts upon the data as soon as it receives it, even if the transmission is not complete. The switch buffers just enough, so not storing the whole thing, just enough to read the destination MAC address so that it can determine to which port it needs to forward. The switch does not perform any error checking, and there's two variants of this type of cut through. Fast forward offers the lowest level of latency, so the latency means lag, so that's got the lowest lag by immediately forwarding packets, reading the destination addresses, because fast forward switching starts forwarding before the packet has been completely received. There may be times when packets are relayed with errors. So the downside is you're not checking for errors. You could be wasting time and effort with error frames. There's also fragment free, which is a bit of a compromise. It's between the high latency of the store and forward and the low latency of the fast forward, because it actually does check a little bit. So let's see, the switch stores and performs error check for only the first 64 bytes. Remember the 64 bytes? Remember, was that something, a significant number that we mentioned before? Was that 64 bytes? Correct, the minimum size. If it can't store 64 bytes, then it must not be illegal. So why forward it? So it waits for 64 bytes, then it knows it's a proper frame, then it does something with it. So that eliminates anything that might be below that, like a run talked about before. Okay, so it does a little bit more. So it eliminates a little bit. Okay, because most network errors and collisions occur during the first 64 bytes, so it's sort of a bit like a risk management type situation. Most errors are going to be in that area, so we just wait for that before we do anything. Okay. All right. So memory buffering. So remember we talked about RAM just then, where we store these frames. We store in RAM, but we can have memory buffering on switches. So an Ethernet switch may use buffering techniques to store the frames before forwarding them, or when the destination port is very busy. Let's just say we got one port which is plugged into the web server, and everyone's accessing the web server, but all these other ports are for your workstations. Not many people are communicating on that, only one. Okay, so you can imagine how the port that's going to the web server is very busy, isn't it? So maybe I can't send everything all at once, because I don't take, it's like a lineup. You send this one, then you send this, then you send this one, then you send this one. So if it's too busy, then what it has to do is it has to store the frames in memory before until it gets the turn. Okay. So frames are stored in a queue that are linked to a specific incoming and outgoing port. A frame is transmitted to the outgoing port only when all frames in front of the queue just line up, like a lineup, is already gone. It's possible for a single frame to delay the transmission of all the other frames in memory because of a busy destination port. So this delay occurs even if other frames can be transmitted to open destination ports. So this port-based memory has that bit of problem. So that's where each memory is allocated to a particular port. So just because one busy port, if we have, let's just put it this way, if we have 24 megs of memory, okay, and we have 24 ports, and if we did port-based memory, you can meg per port, okay, which what if the one port is super busy, or the other 23 ports are not busy? The busy one still gets 1 meg, doesn't it? Whereas all the other 23 are wasting the other 23 megs, don't they? So what about shared memory? Shared memory deposits all the frame in a single memory buffer, common memory buffer shared by all switch ports, and the amount of buffer memory required by port is dynamically allocated. Dynamic means it changes. So in that situation where we have one busy port and 23 not busy ports, we can give the one port more memory. But if that stops becoming busy, we can take it away and give it to other ports. So that's what dynamic means. We can change with the flow of what's going on. All right. Shared memory buffering also results in larger frames that can be transmitted with fewer drop frames. Drop frame is where you lose them. This is important with asymmetric switching. So if you don't know what the letter A in front of any word makes it the opposite. Okay, symmetric means equal. Okay, this side is symmetric, this side they're even, right? Asymmetric means they're not even, not symmetric. So this side might be smaller, this side might be bigger. Think of your ADSL, okay, asymmetric digital subscriber line. Your download speed is a lot faster than your upload speed. That's why it's asymmetric. All right. So basically, it's important. This is important where you have asymmetric switching, which allows for different data rates on different ports. Remember what I said? We could have a switch here with all fast Ethernet, which is 100 megabits per second. But we could have these two ports, which are for the backbone. These might be gigabit. Oh, they're different speeds, aren't they? So, so this shared memory means that instead of actually allocating each one of these equal amounts of memory, we could allocate more memory to the slower ports, which are busier, and less memory to the faster ports, which can get the queue cleared up faster. What about duplex and speeds? Remember we talked about duplex before? Duplex means, half duplex means you can only talk or you can listen. Full duplex means you can talk and listen at the same time, send and receive at the same time. Two of the most basic settings in a switch is bandwidth, the speed. That depends on the type of port. Whether they're fast Ethernet, or gigabit ports. Or you can have 10 gigabit ports if even, okay, it goes up. It is critical that the duplex and the bandwidth settings match the switch ports and the connected devices. If I have a computer that has a 100 megabit network interface card, and I plug in the switch port, which has been configured to work at a gigabit, it's not work. So if I'm plugged into this port and that's 100 megabits, then I'll make this auto negotiate, or 100 megabits. Auto negotiate means it just learns, it works out with the device what speed can we use. Okay. So auto negotiation is a function found in most Ethernet switches, and next it enables two devices to automatically say, "Hey, how fast you want to talk today? I'm feeling a bit tired, so let's just talk a little bit slower. I just had my coffee. Let's talk really fast." You know, that's just a funny analogy, but reality is I'm capable of 100 megabits. Can we talk 100? And they say yes. They decide to use 100 megabits per second. Gigabit Ethernet ports only operate at full duplex. It achieves that gigabit Ethernet speed because of full duplex. Duplex and speed settings. So like I said, if you have two devices, like two switches here, you've got a cable that uplinks them, and one's connected, configured as full duplex, and that one's configured as half duplex, it doesn't work. Full duplex, duplex mismatch is one of the most common problems for performance issues on 10100 megabit per second Ethernet links. It occurs when one port is on the link is at half duplex and the other one is operating in full duplex. It has to be both the same. Okay, it's fairly obvious, because if one's only talking and one's talking and listening, it doesn't work. Okay. This occurs when the port on one link, when one or both ports on the link are reset, and the auto negotiation process does not result in the link partners having the same configuration, or you've gone in and manually configured it. It also occurs when users, that's what I'm saying, a user reconfigures one side of the link and forgets to do the other one. So it's misconfiguration, really, that's the problem. Auto MDIX. So what does that mean? If, in the old days, if I have a switch connect to another switch, I have to use a crossover cable. What does that mean? Because it's the same type of device as this. Okay, so like if I have two PCs, they're both DTEs, data termination equipment. So they're the same type of devices. So I need to have a crossover cable so that the transmitting cables across that so that it's going to the receiving pins. If I have two DC devices, so if there's the same device, DC, data communication equipment, then I also have to use a crossover cable so the transmit gets crossed over to the receive. It's a bit like that telephone game. If I'm talking into the cup, you must put on your ear. Okay? But these days, we don't need to worry so much. We don't need to worry so much because they've got this auto MDIX. So forget about this stuff. If you look at IX, it's straight through or cross. Okay? IX, the I stands for straight through, X stands for crossover. So it decides whether it's going to use a straight through cable, crossover cable. It detects this. Okay, so that's where the IX comes through. Connections between devices once required the use of a crossover cable or a straight through cable. So straight through just goes one end to the other, no crossing. Crossover just crosses over from the receive to the send. Most switch, a direct connection between a router and a host requires a crossover cable still. Okay, if you plug in your computer to a router, one of these routers that is, not your home router, because your home router actually has a switch part of it, you must use a crossover cable. Most switches these days support an automatic medium-dependent interface crossover, auto MDIX feature. When enabled, this switch automatically detects the type of cable that's attached, whether it's a straight through or crossover cable, and it just does its business behind the scenes and makes it work. The auto MDIX feature is enabled by default on switches running Cisco IIS release 12.2. If you're wondering what that is, that's basically the operating system that Cisco devices. Okay? You're probably thinking, Apple iOS, what's going on here? What's Apple got to do with Cisco? Trust me, Cisco came up with it first, okay? However, the later feature could be disabled as well. For this reason, you should always use the correct cable and not rely on this thing. So if it's the same type of device, use a crossover cable. If it's a different type of device, use a straight through. So when I say different type, DTE, at the end of the network, like a computer, like a printer, like a router. They're the ends of the network, aren't they? Whereas a DCE, data communication equipment, is in the middle of the network, like a switch, like a hub, all those kind of things. They're the center. They connect all things together like that.